Maybe it's not intended to.
That's right.
Do you want to check it real quick?
Yeah, just to make sure.
Okay.
No, it doesn't seem to work. The remote function. Okay, now it's working. Okay. All right, that's working. Okay. All right, ready to go. Yeah, maybe we can just start with just introducing each other. I think most of us know most of everybody.
Yeah.
Because it's very small. A couple of 100 kilo, therefore it's not significant. Nobody care about it.
I guess we got most of them.
Good morning, everybody. Thank you for coming to our UTS Brine Resource Recovery Workshop. My name is Ho Kyung-Chun, professor in civil and environmental engineering. I'm very welcome to UTS. I'm sure that we have a little bit of difficult time to find this building. So please relax. Yeah, you don't have to worry about anything. Just have a rest. Now it's the first step. We can introduce each other briefly because you have time to present your activity. So your affiliation and name, and then just briefly you can talk about your background. So and then we can start. So we can start from Nikolai.
Nikolai Vuchkov. I work with DTRI as director of the brine mining program, and I have another colleague here that's with DTRI. He'll introduce himself. But the purpose of what I do there is to develop actually a full-scale project that we'll discuss that is for high purity sodium chloride and also bromine. So I'll discuss the activities, the technologies that we're using, and the approach we're taking.
Okay. Hello everyone. I'm Gayatri Naidu, and I'm a senior lecturer in Australian Research Council, DECRA fellow here with the University of Technology, Sydney. So I guess in terms of my work, I will be presenting all of it later. So we'll talk more about it eventually. Nice meeting everyone in person, finally.
Well, thank you for hosting us. We appreciate it.
Thanks.
So myself, Robert Garner. I think I do know most faces around. The NEOM project in Saudi Arabia. I have a presentation if there's anybody who doesn't know about the NEOM and seen the presentation previously. The challenge being that NEOM has high standards of sustainability, environmental, etc., and has set a requirement for zero discharge of brine back into the Red Sea or the Gulf of Aqaba. And therefore we've been busy over the last 3 years trying to look at ways of valorizing brine streams and converting the whole business model around a desalination plant to a brine production plant with really a byproduct of water.
Chris Corcialis. I am operating as a brine innovation manager in NEOM, trying to provide ideas and options to Roberts and the rest of the team.
My name is Hans Pauwveld. I'm from Coast. I'm the director of the Water Desalination and Reuse Center. We work on a broad range of topics. I will tell you a bit more later on today.
Hi, my name is Jay Chandra. I'm from the Indian Institute of Technology, Gandhinagar in Gujarat, India. And I work on a range of desalination technologies and just got into brine recovery storage.
Hi, good morning everyone. My name is Leonard. I'm from UTS. I'm a senior lecturer, and I'm also working on membrane processes for treatment of brine and challenging wastewater.
Chris East. I'm a researcher at DTRI and general grease monkey, making things research happen.
And he also has one of the most advanced laboratories for brine, for actually measuring rare metals in low quantities in brine. So and I'm sure anyone that worked in that field has faced many challenges. So it will be helpful to learn that kind of experience.
My name is Hamid. I'm working at Texas A&M University, Petroleum Engineering Department. Specifically, I'm working on produced water that coming out with oil and gas. I try to explain some details of some research that we have done for treatment of produced water it when I have time. Thank you.
I'm John Leonhardt. I'm a professor of mechanical engineering at MIT. I direct MIT's Institute level program on water and food systems. I've worked in a broad range of desalination technologies with a particular interest in understanding both energy and techno-economic performance across a variety of systems.
My name is Anthony Christopoulos, also with NEOM, trying to get the clever things that you guys think up into the field and make them do what they're supposed to do.
I'm Shane Han from Qatar University. I'm working at the Center for Advanced Material as the research associate professor. We are making the water technology center, so that's why I had there 4 years ago. So my research area is related to environmental chemical process to use somehow brine to get us some benefit as ion to make CO2 conversion to the formic acid or the hydrogen production. Hopefully I explain more detail in my presentation. Nice to meet you.
Hi, my name is Youngwoo Chu. I'm a Chancellor's Postdoctoral Research Fellow at University of Technology Sydney here, working for Dr. Gayatri. And my background is on polymer, and the current research topic is about development of the selective membrane for rare earth element recovery.
Thank you, everybody. Welcome to UTS and this Brine workshop. So let me start with the acknowledgement of country. So we acknowledge the Gadian people of the Ural Nation as the traditional custodian of the country we are meeting on today. We recognize their continuing connection to the land and waters and thank them for protecting this coastal line and its ecosystem since time immemorial. We pay our respect to elders past and present and extend that respect to all First Nation people present today. So this is our just a brief housekeeping. So we have a fire alarm the exit here. So just in case if you have fire alarm, so you can just go this way. So you'll be very safe. So this building is very safe and sustainable building. I'm sure that everything will be okay. Also, we have a Wi-Fi UTS guest. You can connect, and then the password is RR Workshop 22. So if you want to connect to your iPad or mobile phone, so please utilize this Wi-Fi. And we are sharing the monitors. So if you just put your URL in the your internet site, and you can get the automatic connection of your monitor. So you can share your screen. So some of people just give us your slide, so we can utilize our computer. Otherwise, you can utilize your own computer using these URL numbers. And I'd like to thank you, Gayatri, and then Young, also Leonard and Shahrukh. So they have for this organization of the first UTS Brine Resource Recovery Workshop. So we have a lot of exciting program today. So in the morning session, first session, we have 5 speakers. So Nikolai will start his presentation, followed by Hans and Gayatri, Christopher and Mustafa, and Jai Chanda and Yongwoo. So they will give a very brief their activity, and we will very much focus on today what's the resource recovery. So we just have a very much select and focus of our discussion point. Also after the session, so John and Christos, Rob, and myself, the Hamid and Shane Han, Amit. So some of them are missing in this program, so we will skip, and then we will focus on more next step, what we can do together as collaborators, and how we can proceed with the possible activity in the future. That's the we want to discuss the second session of the discussion. And after lunchtime, and we can have a little bit of technical tour. So we will go to the Bondi Beach and then take a seawater sample and then touch, and we can have a little bit of characteristics of the seawater in Sydney. and we will also have a ferry and then some of the very interesting park, Gap Park. So Watson Bay is a very beautiful area. So we will have a little bit of refreshment, and we have a nice dinner, Italian restaurant near the Opera House. So that's the today's activity. So do you have any questions so far?
Questions?
Yeah,
Thank you for
yeah,
organizing.
questions. Yes.
Can I make a I don't have a presentation because I wasn't.
That's all right.
So
No,
I need to
really
make a
just a
presentation.
I will say a few words about what he would have talked about if he was
that's
here.
right.
So
I can
it-
expand on the things that Nikolai
Yeah.
talked about with some extra developments.
That's
on top
right.
of what he
our
has,
experience
it's not
with
there, but-
measuring metals and
But
minerals.
we kind of come from the same place at this point in time.
That's
Yeah.
all right.
So,
So you can have a more discussion
Yeah.
together. Yeah.
perfect, thank you.
Yes, Sean, just, so if, Christopher, Dr. Mustafa is not here and this last 7 minutes, Ahmad Saleh from SWCC, they're not here, so we
Yeah.
have like, in total, like, about 20 over minutes. So for each speaker, you can expand a little bit more than 7 minutes, you know, just, yeah, you're not so, tight for time.
I think
So
we
it's a
need
bit
to
relaxed.
expand the more discussion.
Okay, okay,
That's
so Sean,
the-
see if you
Yeah,
do that.
that's the
Yes,
individual
keep your
discussion.
7 minutes time,
What
yeah,
I
the
can do
timekeepers
is,
say.
Broad
Yeah.
discussion.
Yeah.
What I could do is talk about also about the PUB program on brine mining, because we're working with them, and it's a new program which there was a lady that's supposed to come from PUB, but she wasn't able to make it. PUB is Public Utility Board of Singapore,
Yeah.
and we're working with them on industrial brine mining, and I'll mention briefly what we're doing. Unfortunately, she didn't make it. We were trying to get her, but
Yeah.
she had some other things that she didn't even know she committed to. In any case, so I'll just briefly mention about it because it's good that it looks like most of the key brine mining activities in the world are represented here by experts in that field, except for the European Union. And we've been also working with the European Union on some of the programs. I can mention what we're doing. But overall, we'll try to use the time, I guess.
That's great. Thank you. How about John? You want to have a question?
I was just gonna say thank you for organizing this.
Thank you. Thank you. for coming.
Thank you so much.
Also, we have a survey result we want to share during the discussion timing. So we have a 10 question we asked to you, and then a lot of people supported this kind of questionnaire, and then we will present our data. And the first 5 questions at the first session, and the second session, Gayatri will present the rest of the questions. That's the all about today. And then just one more question for the recording. So now we are recording this video. So if you have any problem, yeah, we don't have to record. So if you have any issue or no.
So we missed putting makeup on us. We didn't know
You
we'll
still
be
have time, the
recording.
toilet's there,
Yes.
but I can tell you look good. Yeah. Okay. We'd like to take a before photo before we start.
Photo, yes.
Yeah, one photo, yes.
Exactly.
Yeah, yeah.
So let's
Yeah, I'll get
make a
closer
photo
to
time
Gayatri
together.
Yes.
Yep. Okay, ready? 1, 2, 3. Take one more. 1, 2, 3.
Thank you.
Thank you.
So our first speaker is Nikolai Vuchkov. So he's from the Saline Water Conversion Corporation. And then he will talk about the very much exciting project of the sodium chloride brine mining. Please.
Yes.
Go ahead.
Good morning, everyone. What I'll do is we have an ongoing project with Saline Water Conversion Corporation, their research center actually. And as you see, Engie Laborelec on the top, they have been very gracious to join and eventually work with SWCC on the program. Engie is one of the big public utilities in France which have international presence. The project that I'll talk about specifically is a real project that we're developing. We're at a stage of getting close to procurement of large-scale contractor to build the project in Saudi Arabia. So I'll mention what we're doing and why and what are the findings so far. When you look at what's in the brine, the majority of it is 86% in sodium chloride. And just happened to be that in Saudi Arabia, the demand for sodium chloride currently is, the second big industry besides oil is chlor-alkali industry in Saudi Arabia. And they do demand large quantities of sodium chloride. Their current demand is about 12 million tons per year of the entire country for this particular industry. For the Middle East, it's around 30 million tons per year, so it's a significant amount. That's why we focused on it. It's readily available, and we found that we have technologies that can allow us to produce it at much lower price than what currently the market price are for that product. And because the current mines, terrestrial mines for sodium chloride are going to run out in the next 5 to 7 years, which are current source of chlor-alkali industries resource, sodium chloride, they see this just as a perfect timing, almost a perfect storm, where we have big demand in small focused location, and the existing source is going away in 5 to 7 years. So that's what makes this happen. I wouldn't say we could find those perfect conditions in other places, but it ends up to be very interesting here. What we're looking for is two products out of this process. High purity sodium chloride, they need about 96% or higher. Large market, the current price of dry ton of sodium chloride in Saudi Arabia is $65 to $75. Reasonable production cost, we found, and I'll show you how we are looking at ending up with those numbers. Are those numbers realistic? We already have two contractors, very big ones, that are in the vicinity building desalination plants of Jubail, where this project will be located. To verify the pricing, they're giving us about 20% lower prices than what I'll show you. So we're confident with Acciona and Metito being two very reputable turnkey contractors, we could make this actually physically happen from a cost perspective. The demand for this product is from the chlor-alkali industry. There are 4 different main users of the product. We do have contracts signed for 25 years to supply the product to them. So from a commercial perspective, this is also worked out as a realistic project to continue with. And obviously it is most abundant in the ocean brine. One thing we found, because what happens with the quality that they need is we cannot produce it by just going through membrane processes. There are certain impurities that we cannot remove by membranes. And that's why we needed to go through crystallization process. And initially, as everybody else, we look at the crystallization as a evil necessity because it's expensive. But what we found is if we use particular type of crystallizers that create a side product, they call it perch, but it's basically the waste product from the crystallization process. It is very rich in bromine, and bromine is even much more expensive and highly in high demand in Saudi Arabia. So that's why we found that we could actually repay the crystallizer itself by selling the bromine in the waste product. It comes as a bromide, so we do have to treat it to turn it into bromine, and the bromine is the commercial product. But the production cost of bromine is currently $800 to $1,000. We actually worked with a commercial manufacturer of bromine systems, and they gave us a price around $800 to $900. And the demand at which we signed the contract is $3,000 to $4,000. So it's 4 times profit margin to what we see. So bromine is, based on our assessment, just the bromine from the brine crystallizer pays up for the crystallizer in 4 years. So that is what is interesting. I mean, when you look at a problem like this, you turn something that is a real evil in price into something that pays itself back and actually is a profit margin. That's why it's always good to keep in mind that the cheapest solution is not always the best solution. That's how we started with the crystallizer, going the cheapest, but then we started looking at what else can we extract, and that's how we run into the crystallizer that we use, which is more expensive than the average ones that we have on the market, which are used for mixed salts, but on the other side has a very valuable side product. So when we look at the very large high purity sodium chloride market, why does this make sense today? If you think about the salt market worldwide, it's 330 million dry tons per year, so there's a huge market for it. When you look at 100,000 cubic meters a day desalination plant, that can produce 1 to 1.2 million of dry salts from the brine. That's how much we could get, and this is dry tons of pure sodium chloride. Annual production cost of this 100,000 cubic meters a day plant in Saudi, in most countries, is around 60 cents. This is now a fairly competitive number. So the revenue from a 100,000 cubic meters a day plant is about $22 million per year if we just sell the water. When we look at the brine, at $65, which is the low end of the sales price for the brine, that is 65 at a million tons per year. That's $65 million. So we actually have 3 times more value in the brine than we have in the water, which allows us to technically supplement it. And when we consider that this is the sales price, but the profit, assuming production at $40, we have a profit margin of 25 million, which is actually more than what we make out of water. So technically we could subsidize 100% of the water production cost by, and 60% is actually not the water production, so it's the sales price. Water production costs a little bit less. We do have about 20% markup on that. So from that perspective, what we see is with this very realistic project, we see that suddenly brine mining becomes very cost effective. We could completely subsidize and make the desal water the cheapest water in the world, bring it down to zero. The global salt production currently, it is China, US are the biggest producers. India is also a very large producer. In those countries, the cost of salt of the product is lower, around $40. So as you can see, in a place like China or US, we're probably not going to be competitive because that's what they sell it for, not the 65 to 75. But in Germany, in Canada, that cost is $110. So it depends on the market. The markets do vary and the demand for it varies. In the Middle East, it's 65 to 75.
Nikolai, just a question on that. Is that the high purity salt market or the total salt market?
This is the salt market for only for the chlor-alkali industry. This is 100% chlor-alkali industry. We're not considering any other demands. I mean, you obviously have, and what we're producing is 99.6% purity, which can be used also for pharmaceutical, for food industry, but we never looked into them as serious business because their demands are very small. So when you look at the plants, if we're going to build a plant for, let's say, pharmaceutical or food industries, we're looking at 10 times smaller plants. So that's not a sustainable business. For us, the biggest demand really comes from the chlor-alkali industry.
Just to comment on the farmer as well, if you're going to build for farmer, you actually have to have extra, more stringent requirements on your plant as
On
well.
production, yeah.
On your production plant, which we don't
But you
do.
could sell it actually for higher prices. Pharmaceutical industry is willing to buy it at $200, for example, a ton, but very small quantities. So for us, it's not really worthwhile catering to the extra cost to deal with it. When we look at the other product, it is the bromine. Mainly, bromine is widely used as a flame retardant in oil industry. Basically, in every single well in Saudi Arabia, we do inject bromine to suppress potential, the oil well going up on fire. So there is a significant demand for it. And currently in Saudi Arabia, we're looking at 10 million tons per year. Here we are producing significantly less than that. We're producing only about 8 to 900 tons per year. So we're not even covering or scratching the surface of demand for bromine in Saudi Arabia. So how are we getting to develop those two products to commercial quality? The first step of what we do is nanofiltration. And we actually worked with two main suppliers of nanofiltration membranes, Hydronautics and Osmonics, to change their products because their rejection, the main impurity in this case is magnesium. And the main rejection of magnesium is of the commercially available products is 85%. That's not good enough. We need to be close to 90-95%. So they developed or improved upon their products. So now we have two industries, big commercial suppliers of NF membranes that actually can get us to 95% of rejection of magnesium. That is very important because magnesium ultimately, if we don't reject it, we're not going to get good quality for it for the crystallizer even to deal with it. And as a result, we cannot get the final product. So that's really the bottleneck in chlor-alkali industry, magnesium removal. So with NF membranes that actually can do that, now they're commercialized and available on the market, so it's not only for us, but we pushed the envelope to have them developed by those two competitors. The RO membrane then takes a monovalent stream. So bivalent stream currently is designed to go out back to the ocean. We're not doing anything with the bivalent stream in this particular project I'm talking about. This is a full-scale, real-size project. So we're only taking the monovalent stream that comes out of the NF, and then it goes into the RO. RO recovery increases from, currently we're around 33%, 40% because we use different elements. We use hollow fiber elements of Toyobo that are a low recovery, unfortunately 33. So we're going from 33 to, and these elements will not be of that type, they will be spiral wound. Average design 43% recovery. We will be going to actually 55% recovery because of this NF. So we'll be getting more water produced besides concentrating the brine. Once you go through the RO, we will have to go through RO concentrator, And what the RO concentrator does is takes the brine at 70,000 TDS. That's what comes out of the RO as a brine. And it goes into through 3 stages, increases that salinity from 70,000 to 225,000. And we were able to actually pilot test and see we could go all the way to 280,000, but we did not. And what we found is that from a energy perspective, crystallizers do a better job in removing the extra water at that point. If you do cost-benefit analysis, thermal desalination still becomes, or brine concentration and crystallization becomes more competitive than membrane, now at a shift of 225,000. That's why what we have targeted here as a product is 225,000 TDS of brine. And then goes into a crystallizer, which then has the waste stream being very rich in bromine. We extract it fairly easily from that and turn it into a commercial product. And then the other product is sodium chloride. So this is the general schematic of what we have. We are attached to a real plant that's currently in construction, 1 million cubic meters a day. We're located in Jubail in Saudi Arabia. That's on the Gulf Coast. And we call Gulf, people call it Persian Gulf. And depending on the client, it's the Persian Gulf or the Arabian Gulf. But it's the same Gulf. So it is located on the Gulf. We have a conventional treatment with intake, open gravity filters, dual media filters, cartridge filtration, NF. That is where we are removing the bivalent ions and at this point sending into the ocean. That basically is half of the volume of the brine. So technically we're not zero liquid discharge by any means. We have 50% liquid discharge in a way, so we're still discharging the stream. It's very rich in calcium and magnesium, and we're looking at future processing of it. So the brine, a portion of the brine, this 1 million cubic meters a day plant, actually, we don't need all that brine from that plant. We only need 168,000 of dedicated capacity to produce the needed brine. So we're taking some of that brine, sending it to a 3-stage membrane brine concentration crystallizer. We're producing crystal salt. One of our clients is very close that they wanted to liquefy that crystal salt to 25% mass concentration, and then we're pumping that to the final user because it's very close, like about 10 kilometers away. And all the other buyers are buying it in crystal form. This one only is buying it in a liquefied form. But it's liquefied after crystallization, because if we take this brine coming out of here, it cannot meet the magnesium and spec a few other impurities. So we cannot really produce from this system, we cannot produce direct product that's used for the direct use for chlor-alkali industry. This is the location of just to give you a sense of the plant. This is how the plant looks like. The water comes into 2 storage tanks. There are 24-hour storage of the source brine coming from the seawater RO system. Then it goes to MBC plant, that's membrane brine concentration facility. Then it goes actually to those 4 clarifiers are just to shave off some of the magnesium. In the summer, we don't get as good of a rejection as 95%. We only get about 90 to 92%. So magnesium hydroxide is produced here by adding sodium hydroxide and stripping out magnesium to chemical precipitation. That's what this is for. And then the water after that controlled parameter magnesium goes into crystallizers, and from there it goes into silos for dry crystals and then liquefied. And we also have a bromine plant. So it just gives you a sense of the space. So this is a 0.5 kilometer by 1 kilometer, just to give you a sense, again, a space of what this takes to do. Just brief energy use demand components. MBC, membrane brine concentration facility, is by far almost half of the demand. As you can see, crystallizer is the other half. We have the bromine plant, very small demand. Other facilities, pumping, storage, and so on and so forth. So the total demand for this 2 million tons facility is about 117 megawatts. When you look at the 1 million plant, it uses 147 megawatts. So it's still a high demand system. So just for comparison purposes, capital costs, how much things cost. The membrane brine concentration facility is about 163 million, crystallizer about 170 million. The bromine plant is very inexpensive. And then other facilities, again, support storage, clarifiers. So total cost of 144.3, and when we add the NF to it, 34 million, 183 million. And the 2 bids that we've got so far, unofficial bids, are getting us between 420 and 440. So we do have a safety margin from at least 2 bidders that are of very high quality that that make us confident we could make this project happen. So that's it in brief. I know it's 7 minutes only, so there's tons about the detail. But at this point where the project is, we expect to begin procurement, have procurement documents out for EPC contractor to come and build this turnkey by April next year. And then once that happens, we expect 33 months of construction, design and construction. It's a turnkey project. Most of the bidders actually gave us between 30 and 35, so we assume 33 being middle of the road. So this will be operational basically in about 33 months to 35 months. That's briefly, it's a real project, it's coming, and so far, because we have the purchase agreements for the south, we do have the confirmation from the EPC contractors they can build it for this. We believe it is actually physically possible and economically possible.
Just one short question, and then we can go next speaker. Any question to this exciting presentation from Nikolai? Yep.
Just one from me. In terms of that financing, that capital cost,
Yeah.
is that being raised by SWCC? Or
Yeah.
is that through the markets?
The way it is planned is at this point to be SWCC.
Okay.
And there are really 2 paths we're taking. One is SWCC is actually raising funds themselves, including PAF. PAF is very interested. They did review the project already, so they're interested in investing. Out of this 480 million, about 120 million come from the buyers of the cell. They wanted to invest their capital money into it because they are interested. It's a very vital source. They're switching from something that's going away to this, and they want to have actually investment in this facility themselves. So we have 120 million already secured by the buyers of the South. The rest of it, so far we do have about 180 million from PAF, and the rest of it is expected to come from private sources. Now, Engie, that you've seen at the beginning, stepped in recently and said, we're sitting on a pile of money because we're robbing the French people with the new energy, green energy stuff. I mean, it's amazing what's happening in Europe. They have a requirement now for 25% of the energy to come from green power. Engie already achieved that goal, but then went and whined to the government, oh no, we need to increase the price of energy 3 times. So now the French are going to pay it from 12, starting next year, to 33. And they said, we're sitting on a pile of money that we don't know what to do with. We'd like to just come in and invest in it. So the bottom line here is that there are large sources of money. So we've been talking with Engie to step in, and they have a condition, however, to operate the plant. That's why they want to invest. So they wanted to invest the capital and then to operate the facility. So there are a number of interested investors. Engie is power utility, as most of you know them as, but they also purchased all the business of Suez of operating plants. So they have 12 seawater desal plants in operation today that they run, that were used to be Suez plants. So they're in the operations business, and they are sitting on a lot of money. So, and they are very interested in brine concentration because they see desalination. They bought a lemon. Basically, water industry is going down. Prices are going down. It's a kind of a dead end. Water costs, as Rob mentioned, will become a commodity. It will become a side product. Yeah. As we now look at brine as being something to get rid of. So basically, Engie, which are business people, did see that, and they said, well, we're sitting on tons of brine. Our customers, some of them industries, would like to buy it. So we'd like to be in and learn how to operate it. So there is a huge interest. So now we have basically three different big names, Acciona, Metito, and Engie, very much interested in participating in the actual O&M and Engie in investing with capital in the project.
Thank you, Nikolai, and join me thanking the Institute. So we'll continue our discussion. So next speaker is Hans. He will present about the biomining of his eliminating the anti-scallop. So please, all yours.
So when they asked me to give a talk, I didn't know what to present, but we had some contact with Sean, and this is where we came to eliminating anti-scalants. So this was the slide I was asked to make. Is that if I look at my personal research, it's all on biofilms and biological stability in engineered systems. So we look at performance and fouling of conventional treatment, so that's mainly on RO, but we also look at cooling towers, we look at dosages, where I'm going to talk about. But also when the water has been produced, you distribute it to the network, we look at what is microbial processes. So I'm a bioprocess engineer And I don't care what the system is, I just look what happens and how can you improve that it doesn't impact you negatively. So biofouling, this is the slimy bacterial mass blocking the membranes. You've seen pictures like this before, and this is what you want to avoid. So biofouling needs some attention for research. Now we did some biofouling. This can occur at very low nutrient concentrations, 1 microgram carbon per liter. And everybody can calculate it, but to get a sense of how much this is, if you take a sugar stick and you dissolve it in an Olympic-sized swimming pool, then you have 1 microgram. So we really talk about minute amounts of biodegradable compounds in water that can cause biofouling. So you need to have really intensive treatment trying to remove these biodegradable compounds, because you can do tricks to remove the bacteria or try to kill them. But the thing is that the nutrients past the treatment being utilized by bacteria, they start to grow, and that's how you get the problem. So this 1 microgram carbon per liter in the swimming pool gives you 10 to the 7th cells per liter in this whole swimming pool. So just that you have an idea how little bit of nutrient you need to get these problems. Now the thing is that people dose antiscalants to prevent scaling in membrane systems. And we did a study in 2000 where we looked at the potential of 14 different antiscalants used at that time for scaling control. And we looked, could these antiscalants cause biofouling? Now here is the ranking undercoat. This is the publication you can easily find. It was on the previous slide. And what you can see is there's big differences in the growth potential of these antiscalants. So you have to think about up to 2 microgram of carbon per liter. I just showed you the swimming pool with 1. So these antiscalants can contribute when you dose 1 milligram antiscalant per liter with 1 microgram or 2 micrograms of biodegradable carbon. Now what we also did for studies, we selected the antiscalants which are high in growth potential, medium and low. We dosed them to a biofilm monitor at 2.5 milligram per liter antiscalant, and we could clearly see differences in biofilm formation. We also dosed them to spiral wound industrial membrane modules. We took a high one and a low one, and we saw that with the high growth potential antiscalants, you had a rapid performance decline, but also a much more rapid biofilm accumulation. So this is all in detailed in this paper. So that is 2000. But 3 months ago we thought, let's do the study again. So 2022 we again asked for the antiscalants that people used in practice, and we wondered, do people read literature and do they do something with it? Now these are the antiscalants that we tested. So we have phosphonate-based antiscalants and carbon-based antiscalants, and we see that there is still biodegradable nutrients present, and they're even higher than they were when we did the studies in 2020. So if you want to prevent biofouling, then you endorse your pre-treatment. So best to look at antiscalants and select the right ones. Another thing is, why not at some point try to eliminate these antiscalants? I've seen plants where they did the analysis and they found out later that the antiscalant was not even needed. So that could already be a big saving. Another thing is, why not have pre-treatment to remove calcium and magnesium? And that means then also it probably is beneficial for your brine mining when you take it out, because then you don't have the problems with the antiscalants. So this was my 7-minute talk. Thanks.
Just one very short question to him. Yes.
Instead of dealing with biofiling at the outer membranes, wouldn't it be better to remove the feed, the food of the bacteria in the porridge filters, in the pre-treatment? In other words, have a step where you purposefully have biological growth to mop up all the nutrients, so that when it gets to the RO, there's nothing to eat.
Okay, that's one strategy. What people did in the past is they tried to remove the bacteria, so they did ultrafiltration. So they're trying to remove the bacteria, and then when you remove them, people thought there's no growth. But always you need only one bacteria, and then the nutrients will pass in and there will be growth. And then people try to kill, so or they dose chlorine when the intake point and then remove the chlorine or do other components. So, but then also that doesn't work because the nutrients still pass.
Great.
Okay, to remove pre-treatment, this is one of the core research what we do in our center at the moment, because we think there's a lot of things to gain when you optimize pre-treatment.
But
For nutrient removal. Yes.
In other words, instead of trying to remove the bacteria, and that was the strategy all along,
Yes.
you have to kill the bacteria. You have to make sure
which
it's
is technically
sterile.
impossible.
But instead of doing it, not do it.
Yeah.
So the bacteria is there in the pre-treatment, and you active, you promote it.
You have to
so they remove the
you have
nutrients.
to grow the bacteria in the pre-treatment, that the nutrients are used before it goes to the
Exactly.
RO.
Yeah. To answer your question, University of California, Irvine, currently, and I'm working with them, is to develop a process equivalent to activated sludge, but activating marine bacteria to do exactly what you're saying. So you have a reactor upstream of the RO, which is designed to specifically remove. So what we don't want to happen on the seawater RO system, we're actually instigating and accelerating on in a controlled process. So we expect them to report next year about the achievements, but it's marine bacteria are much slower growers, but they could be activated like wastewater bacteria in activated sludge. So what they're developing currently is marine activated sludge equivalent process. And once that is available, I think it will very elegantly solve in biofiltration. In this case, they're looking at biofilters created with a biological zone to do exactly what you're saying, because once you remove the food, bacteria ultimately without food would not be able to grow on your membrane. So you're moving the growth process one step ahead in the pre-treatment.
It's silly.
It's not easy.
It's not easy at all.
Because you need you can easily do a sand filtration. There have been many examples of rapid sand filtration or other things, but that is not enough to remove all the nutrients. So you maybe remove a fraction. It's still giving you biopharmacy.
You need such extensive slow filtration velocities in your
Yes, yes, and that is a matter of cost and space.
But there are ways to do it through basically creating a bioreactor equivalent to what we call activated sludge, but it's a different bacteria and different activation process. It's very interesting. It's very innovative.
So I know of one plant where they have excessive pre-treatment, so with filtration steps, activated carbon, ultrafiltration, and this plant has been operating without any performance decline for over 7 years. So it is possible, but this is a major investment. So it is a kind of tuning. How can you have optimal nutrient removal for a reasonable cost and a relatively small scale system? Now we're looking at this. What is really important is the extent of transfer of nutrients to the surface area where the bacteria can grow. So you need a kind of an RO system for an RO system, but then the RO system should be designed as a kind of small porous material.
One thing that worries me about doing that, and you can have bacteria in a head that works, but what I've seen in Namibia is if that bacteria becomes stressed, they release polysaccharides.
Yes, yes.
And that polysaccharide just goes and blocks your membranes.
I don't want to complicate things, but the thing is, what we found out is that the ratio of carbon and phosphorus in the water can influence this amount of EPS production.
Yeah.
So you have to also look at this ratio of these elements in the water. That's one component. Also, we have done a study where we used drinking water. So it was produced, it is distributed as drinking water. We use it as feed water for an RO installation. Then it still costs us biopharm because this 1 microgram carbon per liter is lower. So there's a lot of drinking waters which already contain this concentration. So the requirements are very tough.
Bacteria are very happy to wait there until it comes to it.
But if I would invest money, I think there would be ways with pre-treatment to remove nutrients to these extremely low levels. So I would put money into this. My own money, right?
Thank you, Hans. Then we go for the next speaker. So Catherine Nate, she will share her activity on the brine resource recovery.
Hello everyone. Welcome to our workshop, and I'm Gayatri Naidu. And today I will present a little bit of my work on brine resource recovery, but before I start, I thought I'll talk a little bit on my background. So in terms of my academic background, I got my bachelor's degree in engineering from University of Malaya, Malaysia, which is also my home country. And thereon I did my master's at Imperial College London, and I continued my PhD here at UTS, and I remained here since then. So it has been a journey, and in terms of, I thought I'll share a timeline in terms of my profile from the time I've been at UTS, since I never left UTS. So this is the positions I've had since I started to where I am today, and also the major research fellowships and external projects that I'm leading as the chief investigator. And so of course then this all boils down to the fact, how does this all relate to resource recovery? So if I'm going to talk about resource recovery, I thought I'll start with where I started my first project, where I was roped in to work on a small scale drinking water production for inland remote area. So I worked basically on membrane distillation. So this was my PhD project and the National Centre of Excellence in Desalination, Australia. And I can't go into the details of it except that this is an interesting project that focused on providing fresh water for a remote indigenous community in Jinjinjara, Western Australia, from natural groundwater sources with a salinity higher than that of seawater, and that's where my interest in concentric treatment started with membrane processes. I work entirely on the application and modeling performance of membrane distillation, and we worked with a team from Murdoch University and the Solar Company. So I can't go into these details except for the lessons I learned in this was translating a lab scale work into practical application was extremely challenging. And of course, working across different engineering disciplines led to a lot of different results compared to what we wanted at the end of the project. And so that was my take home from there. At the same time, while working on this project, I also had full access to Perth seawater desalination, simply because my professor had a lot of projects working with biofouling with the membrane reverse osmosis, and that gave me access to being in the Perth seawater desalination plant. But being a membrane distillation expert, I was very interested more in the concentrate that came out of this desalination plant. Why? Because if you look at Perth seawater desalination plant, it will produce about 80 megaliters per day of concentrated seawater. And at that point, seawater mining was becoming a very hot topic among researchers, and what caught our eyes was rubidium due to its high market price. And being in Perth seawater desalination plant, I had access to the brine. So we tested the brine, and we did establish there was rubidium present, but the challenge was actually an extremely low concentration. Nevertheless, that enabled, through my professor, we successfully received a ARC DECRA discovery project that enabled me to start working as a research engineer on recovering rubidium from seawater. And then on in 2017, I obtained a Chancellor's Fellowship that enabled me to continue my work on concentrate treatment, and then expanded my work into selective rare earth element recovery. And in the later stage in 2020, I obtained the ARC DECRA Fellowship that then enabled me to start looking at lithium recovery with metal organic frameworks. And in more recent times, we also obtained a federal government grant with this is an Australian-Indian project. With this project, we're working with brine treatment technology and resource recovery, and in combination with artificial intelligence. So the UTS team is a cross-cut between our team at CTWW and Professor Michael, who will be here during lunch, who's also our associate dean, working on artificial intelligence, how we can cross-collaborate both these areas with brine treatment and resource recovery. And our Indian partners is from IIT Gandhinagar, Professor Jay Chandra, who's here, and also Professor Umapar. Now, this was the visit that Dr. Jay Chandra had with us last week in our lab, and these are my research team members and postdocs that are working on different parts of brine and resource recovery, and this was where we also work on nanofiltration membrane. We are fabricating and trying to improve the pore sizes to make it more selective for lithium, magnesium, and calcium recovery, and many others. So I thought what would I touch on today would be a little bit more of the expansion of the work we worked on selective rubidium extraction from seawater brine, where we started to where we are today. So when we started, we looked at nanomaterials, potassium, cobalt, hexacyanoferrite. I always been asked this question: why did we synthesize this particular nanomaterial? The reason being that from our study, we know that it was used for removing cesium in radioactive seawater, and given the similar characteristics of cesium and rubidium, so it was highly applicable for rubidium. So the mechanism of this nanomaterial is that due to the chemical imbalance, we produce something which has a highly negative surface charge, and therefore if you drop this nanomaterial into seawater, the cations will be attracted towards this nanomaterial. But due to the ionic radius of potassium that is in the cubic center of this nanomaterial, it exchanges only selectively with rubidium because of the similarity of the ionic radius. And so the only competition factor here would be cesium because of the similar ionic radius, but given that cesium is not present in non-radioactive seawater, so we eliminate a lot of the competition factors, so this was great. And it works well in high salinity condition because the low ionic radius of sodium means it cannot actually go into this nanomaterial. So what's the issue then? So if you look, seawater actually has high concentration of potassium. So in the presence of potassium, so there's something called an ion saturation effect. So potassium cannot actually, it cannot reach its full capacity, and so that was one of the bottlenecks in terms of limitation of this nanomaterial. So in more recent times, we looked at how we could improve the capacity of this nanomaterial, and therefore we looked at if we could synthesize this with metal organic frameworks, so we'd get something that of high selectivity. So the selectivity of both the nanomaterials without and with metal organic frameworks were quite similar. So when we drop this into seawater, in essence, it will only select rubidium. But when we look at the performance capacity with our new nanomaterial with MOF, it actually we get something with about 8 times higher folds for rubidium uptake. And we still have the same issue, but 60% reduction of rubidium due to the presence of uptake due to the presence of potassium. But given the high capacity of this MOF nanomaterial, it's still very viable to be used. But what we found strange was MOF on its own, the metal organic frame on its own is an inert material, so in essence it does not absorb rubidium at all. So we wonder what is the mechanism that that led to this. And so we did a lot of element analysis and particle size analysis. The thing that caught our eyes was that we were able to get a material with extremely high surface area. And so we believe it's something related to the high surface area and the cavity layer of this metal organic framework that reduces the bonding of the hydrated rubidium. Then it therefore enhances the ion transportation within a large surface channel that accelerated the kinetics and increased the rubidium uptake, but that's our understanding of it at this point. But what we do realize is the synthesis procedure of a nanomaterial with and ion exchange material can, there are various MOFs, there are various methods to do that, so we've not reached the point where we can actually understand is this the most optimum material, and therefore we're looking at if we could use machine learning and to understand if we could get results, better results beyond what we can get with a few chemical experiments, and that's where we would like to head to as well. And then that leaves us the next question. This nanomaterial is great, it works, you can drop it into seawater, but it's in powder form. So how can it be practically applied? So we looked at encapsulating the nanomaterial, and this is in using polymer encapsulation. So then we get a conventional column study where we can extract 3 milligrams of rubidium from 12 liters of seawater brine. But of course the constraint is when it comes to a general ion exchange is then there's a chemical regeneration. So we get rubidium, but it's regenerated with potassium chloride. So we get a solution containing rubidium potassium chloride that needs to be further purified. And so we thought look at other alternatives like embedding the nanomaterials with electrochemical electrodes or making it into a selective ion exchange membrane. Then of course that's the question that is we get a rapid extraction within 20 minutes our process can be achieved. But there's less chemical application, but then the constraint is the stability of the nanomaterial and of course the cost of it put together, so there's the cost over the benefit. And then I end by saying that there is an economic viability when we do rubidium recovery, but of course there is also the cost factor. So it all depends on the technology you're using. And of course, if we consider the environmental sustainable alternative to land mining, probably that cost is taken into consideration, then maybe this becomes an economically viable option as well. And we did write a lot about this in a review paper that I wrote with Professor John Leonard's team. And I did discuss this from a timeline perspective, simply to tell you that translating resource recovery into a practical application needs time, grants, funding, and for us is the right teams of students and postdocs. So we always look forward to new ideas and funding collaborations. That's something we hope to achieve through this workshop. So I end here. Thank you.
Thank you, Gayatri. Just one question.
My question. The approach is to target the recovery of rubidium and to target that against its value and then to look at the cost of doing that. But one of the obstacles to doing that is potassium. But what if you also have a business that's recovering potassium? Okay.
I tried that with zeolite. It was too expensive, and it's actually very, very difficult to reduce
What if we
potassium.
tell you that we do have a solution to that, but let's not take more time.
Okay.
We've already figured that
So-
out.
And
We've been tracking what you
whatever
do.
we tried, rubidium went together for this.
Yeah,
We
it
made
is
banana.
interesting.
Yeah,
It is very
interesting.
challenging,
Yeah,
but
it's
it's
the chicken and egg. I have tried a lot of things. Yeah.
Okay, yeah, this is excellent
Thank
work,
you. Yeah,
very
yeah,
much
right.
appreciated.
Thank you, guys.
Yeah, yeah, this is one more question.
Maybe later I can ask.
Yeah,
Yes,
right.
you
I'll
can
just
discuss
go
during
ahead.
the-
Yeah.
What is the market size of rubidium?
So that's a good question. So it's actually a very small market size
In
because it's
Australia or around the world?
around the world. Yeah, yeah, okay, maybe.
No,
We'll
I was
buy-
just,
we'll buy it all.
Only honest to get me
Yeah,
thinking.
for the
All right.
US government.
Yeah, so compared to, if you're asking me to compare that to lithium, rubidium has a really small market application, but it has a very high market price because it's really, really
Because of
difficult.
shortage.
Yeah, the shortage is not with lithium ores, but there is a shortage with rubidium ores because it's actually very difficult to purify and recover rubidium from mining ores, and that's why the high market price.
I would also edge on the side of caution about using statistical data. So we look at the magnesium market, and the magnesium market is constrained. If we can produce magnesium at a cost, the market will grow because everybody will use it
Yeah.
because it's a superior material. So you can't use statistics and look back in history and use that as a basis for saying what the future will be.
Yeah, it will be really the growth of the use of the market because, like for example, as you said, magnesium. Currently, it is mainly used in electrical cars and telephones and shells of computers. But you know, everybody's scratching the surface of electrical cars. I mean, they will become a necessity and the main source. So there will be a dramatic growth in demand. So from that perspective, I think the market will grow with it. And the reality is we don't have it in terrestrial sources anymore. That by itself will drive always the market upwards. So I think we're in the right business to look into, and it's difficult to predict looking backwards because the demand for magnesium basically did not exist a few years ago as much as it is now.
Thank you, Gayatri. We will have a discussion. Otherwise, we are in the behind the schedule, so we can have.
Yeah, we didn't bring our pajamas with us, so.
The next speaker, we have Associate Professor Jaichanda Somnathan from IIT. He will give us his brine resource recovery activities.
Yeah.
Sean, I sent you my.
Yeah, I can load it. Yes. Yeah.
Yes.
Yeah, you can use this one for Nikolai. Can you use the
Yes, please go ahead.
Thank you so much.
Code is okay 172
No, the code for the Wi-Fi.
Wi-Fi. Okay.
That's
R workshop 22.
Capital R.
Capital R W capital as well.
Yeah, workshop 22. Okay. Oh, I didn't know the first two letters. So.
Okay, so I have literally 2 slides, so hopefully I'll help you catch up with the time a little bit. My name is Jay. I'm the Kanchan and Harilal Doshi Chair Professor for Water and Sanitation at the Indian Institute of Technology, Gandhinagar. I'm an assistant professor in the Mechanical Engineering Department. Prior to joining IIT, I got my bachelor's degree from IIT Madras, and I got my master's and PhD from MIT working with Professor John Leonhard. I was also a postdoc at the Tata Center at MIT for a short while. So in terms of the activities that I've been involved with, for my PhD, I was mainly focusing on membrane distillation. So we came up with new configurations of the membrane distillation process, which have higher energy efficiency. So we got like around 3 patents out of it, and this is one of the patents that we are trying to bring to practice in my group currently in India. So this is a multi-effect version of the MD, really small scale, and also trying to incorporate good amount of heat recovery, energy recovery to improve the energy efficiency. So in addition to this, we've also worked on batch reverse osmosis systems to again improve the energy recovery at high recovery. So I've done some modeling work on this to understand the limits of this process, especially for like seawater kind of applications, because usually it's supposed to be very good at high recovery, so brackish water all the way to maybe saturation. And we also have some industrial tie-ups. So this is like a part of a picture from what we've installed at a textile dyeing plant where they are pushing the recovery beyond the 3-stage RO using this system. And finally, I am interested a lot in the analytical side of things. So we have come up with very good first principles comparisons of various technologies. So we did one work on MED versus RO. This was in collaboration with Professor Leonhard as well, where we looked at what is the reason why the RO is dominant, and is there a way for the MED to become competitive again. What we basically found was that an order of magnitude reduction in either the cost or an improvement in the heat transfer coefficient would be required. But the same kind of analysis can be applied to reverse osmosis as electrodialysis. In this case, interestingly, the salinity of the solution also plays an important role. The comparison goes as 1 by S square. So at low salinities, economically it can be feasible, is what we find. And we've also been comparing electrodialysis with osmotically assisted RO for brine splitting applications, because both of these essentially are not like full-fledged desalination processes but can produce water at multiple salinity levels. So that's a brief overview of the kind of work that I do. Related to resource recovery, primarily we have some work that has reached some level of fruition in the dyeing industry, where they have this brine stream which has a lot of salt, and to dye fabric they need salt at different concentrations to dye different grades, like shades of fabric. So for darker shades you need like really high salinity water, and for lighter shades they need low salinity water. So it's a good case study where instead of going all the way to concentrated like supersaturated solutions and then producing salt, can we actually reuse the brine itself in the dyeing process. So this is something that we have attempted, and these are some pictures of we try to understand the color reproducibility after doing this. And also for brine splitting, we are using the electrodialysis and the osmotically assisted RO. In terms of more in line with what we are talking about here, I just started working on lithium recovery. So most of my interest is in the energetics of the entire process. So first we started off looking at the thermodynamics of the process, and what we find is that interestingly, if you do use a recovery solution to split the feed into a lithium poor and a lithium rich solution, and if the recovery solution is like deionized water, the overall process can be spontaneous. So you don't really need to put in any energy into this process, right? But we then focused a little bit more on electrochemical process. So primarily kind of reproducing some work related to using lambda MnO2 as the selective electrode to uptake the lithium on the one side, and using like silver on the other side to take up the chloride, and then reversing the potential to put back the lithium and the chloride into the solution. And here we find a lot of results that try to look at the overall process and talk about the energy consumption being low. But I think the first step here is actually spontaneous, and recovering energy in that step may or may not be feasible. So probably we need to focus on this step, which is where we have to put in energy into the system to actually release the lithium back into the solution. And to understand the energetics of this, it becomes important to model the electrode in a lot more detail. That's something that we've tried to do. And comparing with a few experimental results in the group, basically what we see is that thermodynamically, again, it comes back to this. It is kind of like a energy positive overall process. But practically, we do see a lot of excess work in the charging step. So that's the light red, and the dark red is the lost work during the discharging step. And so perhaps there is more to be done in this space to understand like the energetics of this. And what another thing I'm interested in is maybe comparing this with the adsorbent based methods for lithium recovery in particular, and maybe other solutes also. So that's all from my side, and I hope for good discussion.
Thank you, Jay.
So, yeah, from my previous position before NEOM, I had to deal a lot with textile wastewater from India. Yeah. See, the thing is, at least for salt recovery, for coming from this industry, I think it makes more sense to recover it in order to be used back into the textile, right? Because they use a lot of salts.
Yes.
But what is the problem of using the salts from that you recover from this process? It is the color.
Yes. Correct.
Yeah. And what do you need to remove the color for this?
So that's something like, so when we used NF, so like in the industrial unit they were using like precipitation, so iron kind of precipitation to remove the color.
Electrocoagulation.
Coagulation. Okay.
Electrocoagulation.
That you think is working very well?
With iron seeds, you take out the color, UF, RO with biofouling resistant membranes, and then you can put an OARO, for example, for further concentration. And then you can put the thermal system, which is easy to obtain in the area.
Yeah.
And you can drive all the salts back into the industry, and you can save also the processed water again because the water is a big issue locally. So I think something to, sorry, it's not per se the topic, but I think it could be a very interesting process scheme for this area.
Thank you for a wonderful presentation,
Thank
Jay.
you so much.
The next speaker is Young-Woo Chu. So he will share his activity on the brine resource recovery.
Hi, my name is Young-Woo Chu. I'm a Chancellor's Postdoctoral Research Fellow at UTS, and I'm trained as I'm a chemical engineer by training with a specific interest on the polymers. So especially for my PhD studies, I studied the block of polymers. It's a sort of polymer, but with the two immiscible polymers are covalently linked in each other, so that they microphase separate into nanoscale features. For example, like a cylinder, as you can see here. And since this one is thermodynamically, the pore size is very narrowly distributed, around 10 to the 100 nanometer scales. So we can make a isoporous membrane. That's the main motivation of my research. And another thing I use is the external field, using the magnetic field to align those cylinders to make the tortuosity of the cylinder, to remove the tortuosity of the cylinder, so that make it more permeable. And then, as you can see from this SEM, it worked quite well in the scalable manners. And for my postdoc research, I also interested in the polymer and the ion interaction, especially the cations and ions in the battery systems. I used the lithium TFSI. And I also interested in the polymer and cation interaction, and also the cation and ion interaction, and how they diffuse inside the polymer matrix. So that's sort of the research led me in this UTS with the mentorship of the Biotree. I'm interested in developing a smart membrane, which is highly selective and also highly has a high permeability, and then we can recover the rare earth elements coming from the mine wastewater or the e-waste dissolution. So basically, I'm interested in designing and then novel polymers and some composite systems that will be highly selective to the high atomic number rare earth elements. So, sorry, my slides are very brief. So, but one of the approach we can do is electrodialysis membrane. So, in earlier success from this metal organic framework shown here, the mill system with the PMIDA moiety show that it has a good selectivity towards the rare earth elements, especially the europium. So the Gayatri and our work show that in the zinc ore, there's a high concentration of the europium compared to other brine water. So we had the success in this adsorption system. So using this MOF as an adsorbent. However, in this case, we are working on to make a composite membrane so that this cation the CEM is composited embedded with this MOF to make a highly selective membrane. As you can see, it's and then this SEM micrograph is showing that the composite membrane was well made with a good stability, and our conductivity investigation showing that at the MOF loading of the 48% show the highest conductivity. So we made this composite membrane, did some elemental analysis to showing that the MOFs are well embedded in the cation exchange membrane. So with a brief diffusion experiment at a different pH environment, showing that it permeates the magnesium and zinc, whereas it retains the europium on the feedstock. So this composite membrane can be selectively enrich the rare earth ions in the feedstock. So we are working towards to improve the performance of this electrodialysis membrane. So for the future, since my background is on polymer, I'm interested in making some polymers which selectively coordinates with the large rare elements cations. Also using this selective coat to use it in a MCDI system to selectively electrosorb the ions of interest. So yes, that's all I prepared today.
Two questions. Since this is electrodialysis membrane, you would ultimately, as you're going through the process of selectively removing or passing certain elements, would you have accumulation, and would you need to regenerate as you would with a process of extraction or electrodialysis extraction?
Yes.
That would be still required to be able to. So it will be more of a batch process where the membrane will work, but then you have to remove periodically the accumulated substances on it so you could continue the process.
That's true. Yeah. So this part is acting as a sort of a selectively coordinating site. So if that one is saturated, then we need to regenerate.
And then the other question I have is, have you tried to actually embed these substances into polysulfone membranes, conventional, let's say, seawater arrow membranes? We've done that kind of using the pirate spirit of Florida. They basically take advantage of whatever else other people have done. That's how the pirates work. That's why the state is so rich. So what we have looked at is, and it's an idea that you may have explored or may explore as researchers with UCLA. And when we talk about potassium, as you mentioned, naturally being one of the challenges, what we did is we looked at commercially available ion exchange products. Resins, and we then reverse engineered what is the active substance on those resins. I mean, they're commercially available from big suppliers that are well reputable names, but what technically they have control over from a patent perspective is the resin itself, not the active substance. Most times active substance is a commercial product available with no patent rights. So what we did is we found reverse engineering on some of the key suppliers of this type of elements like potassium ion exchange substances. What is the active substance on that resin that makes it work? And then we, through chemistry, incorporated that active substance into a polysulfone membrane. And what that does is, as the polysulfone membrane would allow you to pass through water, which is how those membranes are designed, they're semi-permeable, we actually also pass through potassium with this substance embedded into the polysulfone layer. So basically what you have, but embedded into the polysulfone layer. And what we found is we were able to do that without necessarily the penalty of the need to regenerate the substance. In this case, it works as a driver for the ions, but potassium ions from the brine side to the freshwater side, but it doesn't have to be regenerated. Mm-hmm. So that basically turns a active substance on a resin into active substance on selectively active substance on a seawater arrow element. And what it does for us It is a very elegant way to combine drinking water production through desalination with concentration. So we've actually developed prototypes on at this point at the level of coupons. And what we would do is we will pass seawater through a first pass, seawater RO membrane. That's first pass. We'll let the permeate go on the permeate side and all the potassium on the permeate side. And then we go through a second pass, which every seawater RO plant has, especially in the Middle East. And that would actually concentrate all this from the permeate. All this potassium will be rejected and be concentrated into the brine of the second pass. So what we end up is all the potassium that's in the water, 99.6% of it, 50 times concentrated into your brine. And you technically have a potassium that is of a quality of fertilizer that is commercially viable. That concept, we found that we can be, we're now reverse engineering all the best products in, of commercial ion exchanges. So I was wondering, as you have substances of activity that for elements that we are very interested in, have you looked into that concept and can you carry it? Because we've found it's actually a very successful way of turning ion exchange, which is ion exchange systems are very expensive. If you want to build a system to do the same thing with ion exchange, it will be 3 times capital cost, plus huge amount of regeneration substance. So that is an elegant way of solving, the capital cost issue, and at the same time, actually, you could implement it into existing seawater RO plant. All you need to do is have the seawater RO elements with the active substance into the polysulfone layer. So have you tried actually to see if you could embed the polymer gels or polymers that you have, the selective, into a polysulfone layer?
Yeah, so this is a sort of a similar approach, I would say. So this, especially this amine group, is when it's attached with this phosphonate acid group that has a selectivity towards the europium. And this polymer gel membrane will be sort of like a ion exchange membrane, but it has a selectivity. So in your case, I'm not. Does it have a selectivity to the?
Yeah, it basically makes the membrane, besides semi-permeable for water, semi-permeable for potassium.
Yeah.
That's what it technically does. And therefore you get permeate, that is drinking water permeate that you normally get, but with all the potassium that was in seawater in that permeate, which is obviously not suitable for drinking purposes. But once you go to the second pass, that permeate goes into the brine. And then that way all the permeate actually ends up 50 times concentrated from what was in the source water with technically no extra energy, no extra nothing. And what we found running for about 6 months, we don't see any accumulation on the surface of these active areas of the polysulfone layer where we have those substances. We don't see any need for regeneration. So just a regular CAP actually can keep it clean. So that concept will be very valuable if we could use this kind of active polymers that you developed and try it, because it changes ion exchange process, which is very expensive, into reverse osmosis process. And we were actually trying to do that on both rubidium and potassium, because we found what are the best rubidium and potassium ion exchange mines, and we are now combining that into one system so we could actually do that. So that's why I wanted to talk to you in more details. But this type of approach, think about it, because what you have is a very valuable substance, and that could be something that you could try and kind of eliminate the effect of ion exchange into, and the person to work with, if you'd like, on that topic of how they made that happen is Dr. Eric Hoyt from UCLA. He leads the membrane laboratory. If you'd like me to get you in touch, he'll tell you exactly what we did, not to have this work as an ion exchange, but to work as a carrier of the potassium. Basically, you are making a semi-permeable membrane for potassium in this case.
That'd be interesting to know, because from my point
It
of
is
view,
very
I
tricky,
think
that's possible.
it's very tricky, because the pore size of your membrane now changes when you put an ion exchange, and that somehow would reduce, or you'll have something reduced on the permeability of the membrane. So I wonder how he got that.
It's a very elegant way, chemical, but we don't have the time to talk about it.
Yeah,
but it's possible.
Yeah,
it
very
is.
interesting
For now,
to
6 months, we've found that it works.
Yeah. Okay.
Go ahead.
Can you explain the spike and then the drop in the pH graph?
I would say it's experimental error.
That's a big experimental error?
Yes, it's huge. But I do not have good explanation, unfortunately.
Yeah.
Yes.
That needs to be looked into.
If I may, concerning the selective capacitive deionization, right? So CDI usually operates at low brackish water TTS. right?
Yeah.
That's right.
So this wouldn't be anywhere near applied for higher cylinders, right?
That's
So
right.
What's
Yes.
the maximum TDS that you have used with?
I do not have a good number, but what we are in the laboratory scale, we are doing at 10 millimole. So that's the concentration of the.
Okay.
Yeah.
So, for example, we could target specific industrial wastewaters with low TDS, but with interesting contaminants.
Yeah,
That's why we're targeting the mining wastewater, because the salinity is very low. It's just high, low.
Mining wastewater is usually
Acidic mine wastewater. So
Okay.
this is it's basically sulfuric acid with a lot of heavy metals. But the TDS isn't that of seawater or seawater brine. That doesn't work for CDI.
Yeah, it's mostly the metals and heavy metals that make it difficult to produce with.
We would tend to do a bit of a precipitation, especially to remove the iron concentration, the Fe concentration, and I guess page 2 to page 5 will already remove a lot of the iron and copper and stuff like that. They're easy to precipitate, and then the remaining metals that we're after, the rare earth element. So one of the main things that stuck with us with this is because this is zinc ore mine it's widely available in Australia, and the zinc ore waste, the slag, only has European rare earth element. All rare earth elements are hard to separate from one another because they have the same chemical characteristics. But this is a zinc ore mine, and it only has EU as the rare earth element. So that's
must be worth something.
yeah, but they're throwing it away. And we're telling them not to throw it away, but the mining industry is very
You gotta
they're
find
not
out what we
interested.
can use European for.
Yeah. So we're like, we can recover this, let's look at this because it's a waste material. Yeah.
Thank you for the
Very
clarification.
interesting. Thank you.
Thank you.
Thank you, Hill. So we have a last presentation for the first session. So Christos Chastias, he has to go. So that in the afternoon session, that's the reason why he want to switch his presentation.
Sorry for taking over, gentlemen. I'm sorry I haven't prepared any slides. I was lazy like that. I will try to keep you entertained with some interesting facts. Yeah. So, the way I see it up to now with my experience in the industry, there are two ways to do material recovery. And we have to think about this ZLD operation in a tri-axis space. Usually, Nikolai already knows that, we used to think these operations in two axes, CapEx and OpEx. The reality is always that we need to add a third axis, and this is the volume of the products that we produce. Yeah, we have to make a viable financial operation. And so you either can do it, you need a big operation like NEOM in order to attract the necessary capital and attract the necessary investments, interest, or the necessary clients. So either you do a concentration of the seawater that leads over to fractional crystallization, or here's the thing, you have a central fractional crystallization unit and you drive a lot of mixed salts to it. Now, there are some operations currently in Europe that actually want to do this. There is a company in Northern Europe that wants to do main fractional crystallization units and have 10 to 20 non-thermal crystallization units all over Europe with using solvent extraction. Yeah, that produces a mixed salt. Then you drive it all up to the main units, and you produce high quality products through fractional crystallization. But you need, for this thing, you need large amounts of salts. But in NEOM, we are more than lucky enough that we don't need to go through this whole shipping operations. We have this big desalination plant the size of a small city, right? And in order to do this, we would like to go through some series of central membrane operations, and this is multi-stage NF, that is followed by RO, that is followed by OARO, or as I would like to call it, is staged assisted high pressure NF, at least for the ones that are using spiral membranes. OARO is a pretty misleading title, if you ask me. Yeah? So it's like an 80 bar NF operation. So multi-stage NF, you take out the scaling potential of the seawater, you improve the lifetime, and perhaps a little bit extra recovery in the RO. Then you put the SANF, stage-assisted nanofiltration, and you concentrate all the way up the monovalent stream up to 250 grams per liter. And then, so you have, remember we're starting around from around in Red Sea, Nikolai, please correct me, around 42K ppm.
42, yeah, 42.
And then you have VNF of around 60 grams per liter, yeah, polyvalent, and you have the 250 grams per liter monovalent. And then what you want to do essentially is fraction crystallization. Fraction crystallization is crystallization step by step that produces high quality salt products, yeah. So you have two lines of fraction crystallization that you can produce, for example, calcium carbonate, magnesium hydroxide, bromine, halide, that's sodium chloride, and potassium sulfate, and that's just the start. Yeah, so we have a lot of potential projects that we can extract, but the thing here is that even if you go ahead and do it, there are potential clients out there that have their own processing operations that produce the salts with the exact specs like they want. So fraction crystallization is not the end of it. Yeah, so it's a necessary evil, yeah, and it has to be partially applied. But there are other processes out there that we are not fully aware of. So again, it's the membrane, because I don't want to take too much of your time. The whole thing is that you have to play it smart, concentrate as much as you can with high efficiency membrane concentrators, and then minimize the volume leading down to fractional crystallization. Because fractional crystallization, it will cost you to both of your kidneys to pay it out. Yeah? And then you need somehow a smart way to provide these processes with the thermal energy they need. Because here's the thing, you need electricity, you need thermal energy, and you need also cooling water for this kind of operations. And that's a lot of OpEx demand right there. Plus, you need all the antiscalants for membranes, for the thermal processes, and also to adjust the pH for the fractional crystallization. And this is something that I would like you also take into consideration concerning the splitting of the salts into acid and base. And what I would like to do is take a side stream of the OARO brine, or SANF brine, and or even the seawater RO brine. I will check about that, and perform bipolar ED. So with bipolar ED, you can split the salts, and that you cannot sell them because they don't have high purity. But what you can do is you can fulfill all your chemical needs for CIPs and for the fractional crystallization. So that's the way I'm thinking moving forward. If you have any questions about what we are trying to do or any other suggestions, please feel free to contact me, or put your questions now. we would like to go down to you need always to go down to the lowest hanging fruits, right? There are some exotic minerals like rubidium, for example, that they are too difficult to extract, and most of, like even lithium, because in seawater, let's face it, they are of a minimal concentration, right?
Well, that's why you have to multiply concentration by price to evaluate them, and that's how we look at them. Yeah, minimal concentration, but a huge price, as you pointed out in your case. So
Yeah.
that brings them up to the attention of why it would be worthwhile, as you did, to pursue them.
Or you should find clients that they really need this mineral,
That's how it
and they are
goes.
ready to pay exorbitant prices to attain it.
Yeah, knock
Right?
on the door of the U.S. government. Talk to me. We will buy everything you've got. So,
Exactly that. So, yeah. Do you have any questions?
Just one short question to Christos. Any question?
No.
Otherwise,
It's okay.
thank you for your great presentation. So now I like to propose a little bit of change of our schedule because we start a little bit late. So if you don't mind, yeah, we have to follow our catering for the coffee and then lunch. Also, we have some visitors during lunchtime. So if you agree, we will do our discussion while we are having coffee together. So we will just have a 10-minute break, and then everyone bring the coffee to this room, and then we will continue our discussion in the second session. So please, we have 10 minutes, right? Please go to toilet, and then get the coffee next room, and then we will have yeah. Please come back in 10 minutes. Yes.
yeah.
So you want to
Yeah, I decided to do.